our input for this black box is going to be 0 to 3. Our output, and our output is just 3 times that much. So we should be able to work out what is our output going to be. Our output is obviously going to be 3 times 0 to 3, which means we can get any value between 0 and 9 in practice. In reality, our outputs are only going to be 0 or 3 or 6 or 9. There are possible outputs, but both of those are stored as binary numbers. How I'm essentially going to draw this up is an input-output table where we've got our inputs. To get 0 and 3, we can have 0, 0, 0, 1, 1, 0, or 1, 1. They're our possible inputs. So I'm just going to put those into my table as my possible input, 0, 0, 0, 1, 1, 0, 1, 1. If I'm labeling these, I could call them A or B or C or D or X or Y, but it's not always clear what inputs and outputs are. So I like to actually just, I'm actually going to call this input 1. I'll call it input 2 and input 1. So essentially, these are my 2 binary inputs, like that thing in Logic Lab that we just looked at that had 4 inputs, and we were doing some sort of digital meter that could output zeros and 0, 1, 2, 3, 4, 5, 6. Again, we had 4 inputs. We have to label them something. Calling them input 1 and input 2 makes sense, and also labeling them this way, input 2 coming after input 1, because in our binary number, if I'm writing out the number like 0, 1, 1, 0, for example, this one here is the least significant bit, which is our units column and our 2's column and our 4's column and our 8's column. So because that number sort of goes upwards, it makes more sense for our input counting to go upwards. So that's why I'm going to call this one input 1 and that one input 2. All right, now, those are our inputs. How do we map our outputs to that? We're obviously going to need to output a number from 0 to 9. How many bits is that going to require? Well, 9 is 1001. So that if that's our maximum number, we're going to need 4 bits to get to there. So similarly, I'm going to call it output 1, output 2, output 3, output 4. Didn't space those out very well, but you get the idea. I can have a blank one that separates out my inputs and my outputs. So now my outputs just have to be a binary number that is 3 times whatever our inputs are. Now this is nice and easy for 0 and 0 because 3 times 0 is 0. And so then I just have to write 0 as a binary number. So that's going to be 0, 0, 0, 0. And then what's 1? 3 times 0, 1 is 3. What's 3 as a binary number? 0, 0, 1, 1. So I'm really just doing multiplication in my head of binary numbers. This number here is 2. 2 times 3 is 6. And what's 6 as a binary number? That's a 4 and a 2 with no 1s and no 8s. And this number here is 3. What's 3 as 3 times 3 is 9, and then writing 9 as a binary number, and I get 1, 0, 0, 1. So what I've done there is taken this left-hand side as my binary input, this right-hand side as my binary output, where my output is just 3 times whatever my input is. Does that make sense? All right, now I'm going to have to represent this as a black box. How do I do that? Well, the next step is to sort of just come up with rules for each of our separate output columns. We've got output 4, output 3, output 2, output 1. Can I come up with a logic statement for each of them? Output 4, for example, is true wherever both of them are true. And so I can just write that as, well, output 4 is true whenever input 1 and input 2. And this column here, output 3, is going to be true wherever, well, we've got input 2 is true, but input 1 is false. So I need input 2 and not input 1. And then here, this one's a little bit trickier. If I want to define it without XOR, but XOR makes this easy, I can use whatever skills I want. So output 2 is going to be input 1 XOR input 2. Or if I didn't want to use the XOR gate, I could write it down as input 1 and not input 2. Oops. Or input 2 and not input 1. So either of those are acceptable. I should point out that for this course, formally, you don't need to know XOR or NAND or NOR. or XNOR, you can everything to get an A, everything required to get an A, you can just use the three basic gates we've seen before of AND, OR, and NOT. But life is a lot easier if you do use the XOR. So here's an example of where using an XOR gate will help you. Not necessary, but it is a shortcut. And finally, this output here, 0, 1, 0, 1, well, that's actually the same as this column here, 0, 1, 0, 1. So output 1 is just equal to input 1. That one's nice and simple. All right, so now I have to draw some black box that has input 1 and input 2, and this is going to have a whole series of gates in there that can get to output 1, output 2, output 3, output 4. And in this case, I can just go through it in any order I want. Input this one is going to be nice and easy to build first because I can just do that. Output 2 is the same as input 2. Output 2 is the same as input 1 XOR input 2. So I can have my XOR gate, which is a gate that looks like that, and have both my inputs going into that, and then have that going straight to output 2. That's that one. Now I can do output 3, which is just input 2 and not input 1. So I need to have a not input 1. I'm going to draw a not gate there and have those two go into an AND gate. Have that go to output 3. And output 4 is just input 1 and input 2. So I can just, there are better ways of doing this, but at this level, we're not worrying about efficiency. We're just worrying about something that works. So I can just have input 1 and input 2 going into an AND gate and having that go all the way to output 4. And I've finished. That's my circuit for my black box that will essentially, I can draw lines around that thing and then say, this is my circuit that is going to map 2 binary inputs to 4 binary outputs, and it's going to just output 3 times whatever our input value is. That's an example of a very numerical one. If you flip the page and have a look at example 3, or scroll down on your PDF, whatever you're looking at, example 3 is an example of a similar black box, but it's not a mathematical situation. I'll just quickly read through that. An evil genius has a hidden passage in his trapped lair. There are a number of sensors in the central room that provide feedback to a central processor in order to test if the hidden passage should open. So we've got inputs that are the light is on, the radio is on, and the curtains are open. And we've got outputs that are the door control and the poison control. So the statement that essentially the description we're trying to solve here is the door will only open if the curtains are closed, and in addition, either the lights must be on or the radio is on, but not both. However, if the lights and the radio are both on at the same time, the room will fill with poisonous gas. So that's a description of the situation that takes 3 inputs and 2 outputs, and we can go through the similar process by building a truth table and then mapping each of those outputs. It really is just putting together all the skills that you've done so far. There's a lot of stuff of logic law simplification. There's not necessarily Carnot maps, but there are truth tables, being able to get from this truth table to each of those separate statements. You're just doing it multiple times if necessary. I'm going to stop there. I'm not going to go through example 3 in more detail, but you can read through that and follow the process if you wish. Example 3's I should also point out example 3 has done things a little bit differently, because what example 3 has done is, rather than one truth table that covers all our outputs, given that we've got 3 inputs, that truth table would have to be 8 rows in size if we wanted it to be. But given that there's 2 outputs, it's possible to separate those 2 outputs into 2 separate Carnot maps and just draw each Carnot map up separately for each output. So that's certainly another way of doing it. This way works better. One truth table works better if we've got only a few inputs but lots of outputs. This Carnot map way will work better if we've got only a few outputs but lots of inputs. So balancing that is something you'll get better as you practice these skills.